So as you look at these alternate bases other than e, know that they're basing it off of this definition right here. A to the x equals e to the natural log of a x, all right? And the reason it's multiplied is because when you have base times base, right, you multiply the bases. So some basic functions of logarithms, which are true, are bases and exponents. Anything to the 0 power is 1. When you divide like bases, you subtract their exponents, multiply, you add, power to a power, you multiply. That's something that I think we've known since like Algebra 1. Half-life. So the half-life of carbon-14 is about 5,730 years. If 1 gram of carbon-14 is present in a sample, how much will be present in 10,000 years? So half-life, you always have a base of 1/2, right? Because that is your half-life. It is to time period over every 5,730 years. So however many years you have divided by 5,730, that's the power to which you will have taken 1/2, that many times, right? So if they want it for 10,000 years, you're just going to say, well, 1/2, 10,000 years. That is basically what half-life means. 0.3. So in 10,000 years, you'll be down to like close to 1/3 of that 1 gram. It takes a long time for that thing to break down. So we have defined this differently before, log base a of x. The reason it does this right here is change of base formula. If you remember your change of base formula, change of base is that if you take, and so they're just writing it a different way. If you take log of any base of any number, you can write that as the log base 10 over log base 10 of a, or natural log of b over natural log of a. So that's your change of base formula, if you remember it, right? So that's all this actually is. Log base a of x, well, that's just the natural log of x over the natural log of a. It's just change of base. And so that's just change of base property that you have been accustomed to. They're just writing it a little bit differently, and they're using natural log because we're going to pull this into our differentiation and integration. Properties are the same. Y equals a to the x if log base a of y is x. Your bases cancel out bases, so base a will cancel out log base a, so that's just going to be what that is, x. Log base a will cancel out exponent base a, so that will also give you x. So bases cancel out bases pretty much, like bases cancel each other out, which we just did with natural logs. It was just base e. So when you're solving an equation, it's something like this, you don't even have to rewrite, right? Because we know that's to the 4th power, and we know that it's in the denominator, so it's to the negative 4th power. So we know that x is going to just equal -4 here because that's a perfect little thing. If you wanted to calculate this, then it may be easier to write it in exponential form. So then base 2 exponent 4 equals x. Then you know that's going to be 16, and because it's negative, it's going to be in the denominator. So sometimes you can rewrite it like this one, and it'll help you. Sometimes you can just see it, that, hey, what do I take it to a power? It's going to be in the denominator, so on and so forth. So it just depends on which is easier. Some of this will come into play when you're doing your differentiation, because you'll have to realize I can rewrite it to maybe get it to something simpler. All right, so derivative for something other than base e. Something other than base e. When it's just something, a base to an x, it's just going to be a to the x times the natural log of that base. Now, this is actually the same exact thing that we did with e's, except your e's canceled out. So if I wanted the derivative of e to the x, it's just e to the x. Well, because if I added in that natural log of e, well, that's just 1. So it's just e to the x. So it's actually the same exact formula. We just didn't bother putting ln of e because ln of e cancels each other out to a 1 and you're done. So you have to add in this natural log of that base, which is true of e, but you didn't need to worry about it. If you have a function other than x, so let's say we have something in there that is not just a to the x. Let's say it's a to the x squared or a to the 2x plus 1 or something like that. You still do a to that, whatever it was, you multiply it by a natural log of the base, and then you have to multiply it by the derivative of that exponent. Think of the chain rule, all right? You have to do the derivative of what was inside. So how does that translate when you do logs? Derivative of a log of something other than e, so log base a. It's still, so remember natural log was 1 over x, right? Derivative of natural log is 1 over x. So we still have that 1 over x piece of it right here, but then we are multiplying that denominator by the natural log of that base. This is identical. It's just if it's something other than an x, you have to include that derivative of that exponent. And they have the proof here by using the definition that we talked about of a to the x. It works because we can rewrite it this way, and you will get that natural log. You'll basically get the chain rule is what you'll get when you do this. And so it pretty much derives from the chain rule. So let's look at some examples here. They are really, really simple to do. If I want the derivative of this, it's going to be exactly what it was. And then natural log of 2 thrown in there. So natural log of 2 to the x. For this one, it's going to be 2 to the 3x. I have to do my natural log of 2. I also have to multiply by the derivative of that exponent, which is 3. So you would have 3 natural log of 2 times, and you could put parentheses here, however you want to do it, 2 to the 3x. That would be my derivative, right? Cosine, all right? So if you think about what you have to do, the log of the cosine of x, you're still going to have 1 over your cosine of x. You do have to worry about your base. So you do have to say your natural log of 10 there, okay? And then you have to multiply the derivative of this, which so you'd say times negative sine x. So for this one, you want to simplify it a little bit more than this. Sine x over cosine x, right? So these two simplify to negative tangent, right? So you end up with like the negative tangent of x over that natural log of 10. See? So it's very, very simple in executing it. It's pretty much just going backwards. So the integration of a to the x is just a to the x. And then you have to multiply by 1 over your natural log of that base plus c. So for this one, it's going to be the integration of 2 to the x is just 2 to the x, but we do have to multiply by 1 over your natural log of 2, and then, of course, plus c. So you could write it 2 to the x over natural log of 2 plus c. That's easy. You just have to remember it. Some examples here, comparing these. The derivative of e to the e is just 0. Why is that? Well, e to the e is a number. It's a number to a number. It'd be like the derivative of 2 cubed or 2 squared or 3 cubed. That's just a number, and the derivative of any constant is 0. The derivative of e to the x then, well, that's just e to the x. This is different though. E is a constant. So x to the e is just like x squared. You would multiply by the 2 and subtract 1 from it, right? So you're going to multiply by your exponent and subtract 1 from it. E is a number, right? 2.1714. I don't even know the whole number there. It's obviously non-repeating, non-terminating. Look at this x to the x. So this is the only guy that's a little crazy. Y equals x to the x. There is no really nice way to do this. So we're going to use our natural log expansion here to do this particular one. By that I mean we're going to do natural log of both sides. Then we're going to take the derivative of this. And so when we do the natural log of both sides, we get y prime over y. Obviously, we're solving for y prime. This then can expand. We have x natural log of x. We can use our product rule. The derivative of the first is just 1 times the second plus the first derivative of the second, right? And so then we have the natural log of x plus 1. Y prime over y, we need to multiply by this guy. Right, so multiply both sides by that y. And then, of course, replace your y with what it originally was. So I have natural log of x plus 1 times x to the x. And there's really no simplifying that. I mean, you could distribute them if you wanted to, but it doesn't really help you. So you can leave it like that. Right, so they talk about limit theory here, and then you start seeing that the reason you have this whole E in your PERT is because of limit theory. If it's continuously compounding, so basically they're saying it's typically raised to the number of times per year times the number of years, right? Well, all of a sudden the number of times per year is continuous. Well, continuous is infinite. Like if I said, what are the numbers between 1 and 2? That would be an infinite set of numbers. You could not continue to tell me the numbers between 1 and 2 if I'm talking about rational and irrational numbers between 1 and 2. And so this is where the PERT formula even comes from, is that all of a sudden you see that this piece goes to E. And so then you have this E to the RT that is multiplied by your principal. So this is the development of the PERT formula that we have known. It comes from limit theory. So it comes from limit theory of calculus. And we know how to do it. We know how, I mean, this is pretty straightforward. Deposit, that's your principal. Annual interest, 0.05 into 5 years. And then compounded quarterly, your N is going to be 4. Monthly, your N is going to be 12. Continuously, you're going to use your PERT formula. And so you're basically going to use one of those two formulas. Your A is going to either equal the principal 1 plus your rate over the number of times per year, either quarterly or monthly, depending on what you're doing, raised to the same N times the number of years, or continuously, you're going to do the infamous P E to the R T. And so this is a formula that is based on limit of in calculus. Thing that you will always see with these wonderful growth formulas is bacterial growth, also one of their favorites. And it's just like this one actually gave you the growth function. So there are going to be times when you're actually going to use the same PERT function. The initial amount of bacteria, the rate at which it was growing or decaying, depending on what you're talking about, and the number of days or hours or whatever, if they're talking about reproduction and, fruit flies, it'll be, okay, every hour, it reproduces this much rate or whatever. And so recognizing whether you're going to use a basic formula like a PERT formula or whether they hand it to you and they actually say bacterial growth is growing according to this function. Y is the weight. T is the time in hours. Find the weight after 0 hours, 1 hour, 10 hours. What is the limit as T approaches infinity? And so then they're wanting you to then say, oh, well, this is going to be E to the negative 0.4 times T. Well, E is approaching a negative infinity, so that piece is going to be approaching 0 because it's going to be in the denominator that my infinity is growing. So E over some infinity is going to, this whole thing's going to approach 0. So it's actually going to just be, as it approaches infinity, it's going to be 1.25. So it's kind of interesting. You would just plug in 0, plug in 1, plug in 10. That's really easy. This guy, this is where it gets a little bit trickier. 0.4 to the, and we're talking about this moving towards infinity, right? Well, that's to the negative power, right? So we're going to just look at it each piece. That's going to be 0.25 over E to some infinity, right? E is getting E to the power. it's 2.1 whatever, taken to a huge power. This guy's staying the same. So this piece is moving towards 0, right? Because 0.25 numerator is staying the same, denominator is growing infinitely. So we're going to get this number that's getting smaller and smaller and smaller and smaller towards 0. So you end up with 1.25 over 1. So what is the limit as it approaches infinity? Well, that's just your 1.25. All the other ones, you just plug in.